In order for us to completely describe our random variables and the probabilities associated with our random variables, we have a set of descriptors that help us compare and contrast, in one case, one random variable with another random variable, and also we can compare and contrast the probability density functions or mass functions, as the case may be, for an individual random variable. We may decide, as we'll see in another lecture, that we have things called a normal distribution or a log normal distribution. So we may want to compare and contrast the difference between having a certain random variable take on a normal distribution versus a log normal distribution or other distributions, as we will see in upcoming lectures. The first most common descriptor is the mean value, and in the context of this course, we will be using the term expected value for the mean. This is a term that is commonly used in statistics circles, where we apply what's called the expectation operator. And the expectation operator is symbolized in our textbook and elsewhere as well with a capital E in parentheses and then the random variable, or what the expectation operator is actually working on. In this case, we are taking the expected value of the random variable x. Works in both discrete and continuous cases. For the discrete case, we have the summation of the individual value x sub I times the probability that x sub I shows up. We multiply that and then we sum it to other values over all of the possible values of x sub I. This gives us the definition in the discrete case of what the mean value is, or the expected value. This is the expectation operator applied to our random variable. For the continuous case, we have the definition, similar definition as we've seen before, where now we're applying the integral from minus infinity to plus infinity of the value x times the probability of x taking on a specific value or a range of values for continuous, then dx. This gives us what is the mean or expected value, and you can see that is really a weighted average type of value. It's a weighted average because what we're doing is we're applying the value times the probability that that value shows up, and we're summing it up over all of the values that for the discrete case, or we're taking the integral in the continuous case. And that is what really a mean value is. So what you're used to determining a mean value for a set of data, that's really something a little different. That's called the sample data, the sample mean, and that is different because it's just a subset of all the possible values, and it's not the same as what we're talking about here. This is the mean value of a population of, or a random variable, the population of the random variable. In the discrete case, the set of all the values that it can take, or the continuous case, from minus infinity to plus infinity. The notation that the textbook uses for the mean value in this case, or in this context, is mu sub x, where this is again the capital X representing the random variable under consideration. And this is the expectation operator E applied to our random variable x. The mode is the value of our random variable x with the highest probability. We can illustrate this with the PDF at the bottom of the screen here, where we have some probability density function. In this case is continuous, but we could also apply this to the discrete case, where we have a continuous PDF. So the probability density is on the y, and then the random variable x is here. And the probability, that's the highest probability, is in this area here, and I've just arbitrarily chosen what I feel, I've just pulled off the graph rather, what I feel is the highest point, and this would represent the value of x that is the mode. It has the highest probability. Okay, again, a little bit different from what you probably learned in lower level courses, either in high school or maybe even freshman, where the mode is just simply the number that represents the one that shows up the most often. Okay, this is a more specific definition in our context with the value that has the highest probability. The median is the value of our random variable where the CDF is equal to 50%. So remember, this is the representation of what the CDF function is. F, capital F sub x, this is our random variable x, for our value x. And in this case, we use the notation x, small lowercase x sub m to represent the median. And where this is equal to 0.5, this is the median value. So at 0.5, so this is our CDF. Remember all the rules for the CDF. Starts at 0, ends at 1, has to be continuous, has to be increasing. We have, at some point, it crosses at 0.5 or 50%, and the value of x, where it does that, is the median value. So the expectation operator doesn't just work on random variables. It can also work on functions, and we'll see these a little bit later in our discussions. But for now, because we've introduced the expectation operator, let's apply it to a function. So if we have a function g of x, where g is a function of our random variable, we can take the expectation of that. And just like we did with the random variable in having the expectation, we do the same thing, where now we take g evaluated at x sub I for the discrete case, we multiply that value times the probability of x showing up, at x sub I showing up, and we sum those over all x sub i's. Or for the continuous case, we have the integral of minus infinity to plus infinity of our function g of x times fx of x dx. This gives us our expectation for a function. And again, we will see this a little bit later on. We also want to measure what's called dispersion, where dispersion measures or quantifies the shape of the probabilities that are associated with our random variable. So for instance, let's say all 4 of these plots here represent a random variable probability density function, a PDF. All of these are shaped differently, and what we can do is describe them with certain attributes that will give us an idea of what shape they take. So it's a way of measuring how they are dispersed, how the probabilities are dispersed, because we can see here clearly that the PDF of this one is very different than the PDF of this one. Variance is one way that we do this. It tells us how spread out a PDF or a PMF is. For the discrete case, we have the variance of x. This is the notation that we use. Variance of x is equal to a value x sub I minus its mean value. We take the square of that difference and we multiply it times the probability that x sub I shows up. And then we sum it over all of the possible values of x sub I. In the case of the continuous random variable, the variance of x is the integral from minus infinity to plus infinity of x minus the mean value. We square that quantity and multiply it times the probability function fx of x dx. We can derive another form of the variance if we expand this out a little bit. So we take this square here, what's in the parentheses, and we FOIL that out. If you remember that from your days of algebra. FOIL this out, and we end up with x squared minus 2, the mean, times x, plus the mean squared. Now, if we multiply or we distribute this, our probability function fx of x, out along through this parentheses, we end up with x squared times fx of x. Now, this is the expectation operator acting on x squared. So we write that notation as ex squared. And we do the same. We have minus 2 mu x times fx of x, which x fxx, remember, is the expectation operator acting on x. And then we have plus x squared. Now this term right here is mu. Right? This is the expectation of x, which is the mean value, so we end up with mu sub x squared. When we reduce this, then we end up with this form of the equation, which actually works for discrete or continuous functions, where the variance of x is equal to the expectation of x squared minus mu of x squared. The expectation of x squared is what we call the mean square value of x, sometimes referred to as that. So this is the variance. This gives us an idea of how spread out our distribution is. And the standard deviation, which you've all heard about, but strictly in definition of it, is the square root of the variance. So the variance is described in the previous slide as the expectation operator acting on the x minus the mean, and the square of that times the probability is the square root of that that result is our standard deviation. Another important term to keep in mind is what we call the coefficient of variation. The coefficient of variation, or C dot O dot V dot. And we use this because we do not want to confuse it later on with what's called the covariance. That's different. And the covariance is often COV, people write down. So if we write explicitly C dot O dot V dot, we're talking about the coefficient of variation, and your book, to avoid that confusion, introduces delta. So delta x, this is a random variable x, is equal to the standard deviation divided by the mean, or the expected value of x. And this, of course, has to be for means greater than 0. Otherwise, we are undefined. This gives us an idea of how the standard deviation relates to the mean. The standard deviation by itself is just a number, but it doesn't tell us anything if we don't have kind of grounded in knowing where the values are actually lying. So a standard deviation of 100,000. Well, that sounds like a lot, but if the mean value turns out to be 10 million, then a standard deviation of 100,000 it's going to give us a very low coefficient of variation. So therefore, we know that the probabilities are not spread out that far. At this point, I suggest you take a look at the video and in your textbook of example 3.4. Okay. We've got some lesser used values that we talk about. The first one is the skewness, and although it's defined by, instead of taking the second or the square of this difference of x minus the mean, where the second was for the variance, well, the third is what we call the skewness. and there's also your textbook also shows the discrete case, where this is just the continuous case, but this is nothing more than the cubed of the difference between x and the mean. Again, the integral for the continuous. And what this does is it tells us how things are leaning. So a probability density function here on the left-hand side, this would give us a positive result, a positive value, because we are cubing, so we're going to end up with plus or minuses. A positive skewness tells us that the densities tend to be weighted more towards the lower values, whereas a negative skewness tells us that the values tend to be weighted more towards the higher values. Right? So it gives us an idea of which way things are leaning. And then there's also a kurtosis, and a kurtosis is now where we take the fourth, the quad of the difference between x and the mean. This is not used all that often, and for our purposes, both the skewness and to a much lesser extent the kurtosis will be discussed further on. But I do want to make you aware that it's out there, and this is what it's talking about. In this case, the cubed difference is what we call the peakedness. It gives us an idea of how peaked or how pointed the probability density function is. All of these have an analogy with geometric properties. You're all very well familiar with things like the centroid and the moment of inertia. We call all of these measures moments because of their analogies to our center of gravity and moment of inertia. So if here we just have a variable x plotted onto y, we have some function y is equal to f of x, and the center of gravity of this shape is going to be located at x sub 0, so the centroid rather is going to be at the center of gravity, and the centroid is defined by the integral of x times the function f of x dx. So this looks very familiar to the expectation of x, the mean value of x. And as a result, we call this the first moment. So often you'll hear people talk about the first moment of a random variable, and all the first moment means is simply the mean value or the expected value, and it's due to this analogy with the centroid calculation. And likewise, as we go up, we've got the moment of inertia, which is going to be x minus the location of the centroid, squaring that, and we times that to our function fx dx, and we take that integral. So the variance, this looks very much like the variance, so we say the variance is the second moment. And people also say the third moment and fourth moment for skewness and kurtosis, but again, our discussion will really focus just on these first two moments.